All right, yeah, so hey everyone. So those guys that don't already know me or report that are getting to see some broken stuff there. Typically, we do a lot of like web app stuff or application, but lately we've been getting a lot of embedded work, and a lot of that is low level. So I kind of came up with the idea of a pretty easy and approachable way to get into binary exploitation. So I was telling Mike earlier, I originally had this whole presentation set up, and I had all these slides and all these examples, and then kind of like a few hours ago I decided to just scratch all that because it was probably the way I discovered what this should be for introductory level. So a lot of this is probably going to be a bit impromptu and kind of weird, so it's either going to be really good or just time fire. So we'll see. So some action set. So when you start getting into exploitation or exploit development, or even just looking at binaries at a low level kind of reverse engineering standpoint, you start hearing a lot of stuff. So buffers and stack and heap. So what is all that? Well, a buffer is basically just a temporary storage location. This can either be predefined or it can be dynamically allocated. The stack is really just an abstract structure that stores information about the current routine. And by routine, you typically are referred to the current program. So that's the way to think about it. The heap is, it kind of works alongside the stack. The heap is really just a freeform region in memory that you allocate dynamically. So a way to think about that is, if the stack has information of pointers and addresses in memory for where certain things live that the program is going to use, the heap is kind of where you would allocate new space for, say, an array that's going to store some user-defined string. So all of this too, I'll get into a little bit more detail. It's a lot of information to cram and not a lot of time. So if you have any questions, feel free to ask them. I may not get to everything. So when you think of memory, when you think of programming, really, it all comes down to this. You have a space in memory. The memory is segmented into different chunks. Each chunk of memory is used by a different piece of the system. So here we have a basic representation of how memory is going to be split up. So at the top you have kernel space, and that's really going to be kind of your operating system. That's going to be different things that uses undo its kind of runtime environment, that type of stuff. And then you have from the bottom up, you have your text segment, which when you're actually thinking about a program that you're running, the text segment really refers to the code. It's where the binary is stored, or where it's referenced from. This section of memory is read-only, and basically the reasoning behind that is, okay, so you have a binary that's running in the space, or at least the instructions for it is stored in the space. You don't want anyone or anything to be able to overwrite that, because then they can basically just write a program on the fly. Above that, you have the data segment, and this is where uninitialized variables are going to live. So say at the top of your int main function, you have like a character array for someone's name and then for their age, and they're all uninitialized. That's where this is, and later be initialized. So the BSS segment is where uninitialized static variables live. Sorry. The BSS segment is where uninitialized static variables live. The data segment is where the other variables live. And then you have really the stack and the heap. So you can kind of just ignore that middle piece for now. That we're going to just pretend that's something. So the stack is going to go down and the heap is going to grow. So I kind of already explained what the stack and the heap are. The reason they grow towards each other is really just for efficiency. So you have a space of memory that's allocated the heap can kind of grow or shrink as it wants without really affecting the rest of the space, if that kind of makes sense. The reason I said just to kind of get more of this stuff here is because while it's technically separate from the stack, what that really is just, it points to your different libraries. So the example here is like libc. So the way linked libraries work in like the Linux environment is that you, I guess without getting too technical, essentially you have a linker layer that's going to go out and fetch all the different libraries and all the different information you need. That's really the gist of it. So that's what this is referring to. Okay, so as I said, the stack is really just an abstract structure that represents the current program that's running. So the stack is a LIFO structure, which means it's the last in, first out. So when you think of the stack growing downward, every time you push an instruction onto the stack before the preceding instruction can be called, the current instruction has to be called off the stack. So you layer it down, and then in the order they were layered down, the last one that was added has to come out before the one before that can be called overrides. So the stack goes downward, so that means lower addresses are at the top, higher addresses at the bottom. Sometimes, like in certain books, you'll see that reverse. It's kind of confusing, but for within the bounds of this presentation and all of my examples, just think that the stack goes downward. So 0x0000 is at the top, and then 0x is at the bottom. So I already said the stack and heap go towards each other, and I kind of explained why. The stack is static, and it's considered faster than the heap. Well, it is faster than the heap. It's static in the sense that you're not dynamically allocating any more memory. In the heap, you are, and that's kind of why it's a little bit slower. And when I say dynamically allocating memory, think like malloc. So you're gonna have a buffer, some sort of buffer, or you're going to have some space in memory and you want to allocate X bytes. You're going to call that function and you're going to tell it where you want to allocate this memory to, or where you want to point it to, and how much of it you want to allocate. All right, and then super quick, we're going to go over the X86 architecture, and this is really just kind of a crash course on it. So it's a register-based architecture, and what that really means is just that you have well, really, you just have different registers. All these registers are again, just more spaces in memory. When you think of memory, just think of a huge array, and each block is just a new space. So these registers are going to do different things. They have specific purposes So let me explain this way. So there's the general registers, which are AX, EBX, ECX, and EBX. So EAX is the accumulator register. So that's like the general purpose register. ECX is the counter. So really, at a very low level, when you think of the counter, it's kind of like the I in the for loop. So you have like for I equals 0, I equals, well, I is less than something, I plus plus. This is kind of the same thing. So it's just going to accumulate its value until it reaches a certain condition, and then something is going to happen. I forget what these were called. Again, but it doesn't really matter. The general purpose registers, they're going to be used for various amount of things during your process, and that's actually something that we'll get to a little bit later. And then you have your index and your pointer registers. So you have your stack index, your base pointer, and your stack pointer are kind of like the big ones. So the base pointer is going to point at the current instruction, I believe, and then the stack pointer is going to point at the current instruction or the current point in memory where you're running, and then the base pointer, I believe, is going to be the return address. And then you have a bunch of other things. So you have like segment registers, and you have flags, which then get split even further, which we're not really going to worry about right now. That's really just kind of there for completeness. And so when you're looking at assembly, you're really just a disassembled binary. If you look at it on X86, which is 32-bit, or X64, it's going to look a little bit different. The big thing is, yeah, okay. So the big thing is that registers, everything on your right here would be the 32-bit equivalent of the registers. Everything on the left here is the 64-bit equivalent of the registers. They kind of encapsulate each other. So if I go back here, you can see that EAX has kind of a sub-register that's AX, which would be the upper 16 bytes, or 16 bits, sorry. And then below that is AH and AL, which are going to be the lower 16 bytes, and then the upper 8 bits, and then the lower 8 bits. When you look at a 64-bit register, RAX encapsulates EAX, and then the upper 32 bits are going to be RAX, while the lower 32 bits are EAX, and then it gets split further. Okay, cool. So, a couple of things that are probably useful to know when you're just trying to get into this. So, GDB, which pretty much is distributed with almost every modern distribution of Linux, or really any other debugger or disassembler. I like GEP, which is really just a wrapper around GDB, which I'll show you guys in a second. It just gives you a little bit more information on one screen and kind of provides more flexibility. If you have deep pockets, you can go for IDAP. I don't know, I think it's like a $4,000 license, but it's like the tool, super handy. Something that's a little bit more accessible, Binary Ninja, which I think a student license is only like $100 or it's not very much. It's nice. They get the job done. It'll do X86, X64. It'll do some ARM stuff and then some other weird stuff too. So it's kind of nice. Object dump. It's super handy when you want to just quickly get the assembly for a binary, or just dump it and just kind of start sniffing through and get an idea of what this thing is doing. Some sort of scripting language is probably going to be helpful, really just for automation. So Perl or Python. I personally like Python, although sometimes, depending on the environment, Perl comes in handy as well. Along those notes, when you actually get into like exploit development and actually kind of packaging something up, so it's kind of like a one-click and go. There is a library for Python called Tools, which I'm not really going to cover here, mostly because we're just not going to have time. We're going to do an entire presentation just on that. But it's nice because it provides a lot of support for actually, I guess, really just creating exploits. So it has like built-in shell codes that you can just assign and use. It has a whole bunch of other things that are super, super nice, just to automate the process. An understanding of native code, or at least just a basic understanding to get started, is pretty much required. So, C or C++, understanding how that works, and understanding how something that's super low level interacts with memory in the processor is really just going to make your life super, super easy, because you're going to come across a lot of things where you don't know why it's doing that until you actually understand how these things interact. Some basic assembly knowledge, again, pretty much required. And then an understanding of the system architecture is handy. So, for example, if you're working in a Linux environment, it's kind of nice to know and understand how the Linux kernel works, why certain things happen when other actions occur. It's really just, some people are working in a Windows environment, and if you've ever done any binary work in a Windows environment, pretty much everything is an acronym that's like impossible to understand. In Linux, it's a little bit different. So just knowing your environment works. I'm sure I'm missing a whole slew of things here. But again, this is kind of the last thing that I put together, just like basics. And yeah. So, I guess we can start talking about actual exploits now. Probably because you guys are here. So, I don't actually have any examples, and there's a reason for that. So, let's see. Okay, so, Mike, you guys did your thing on, like, capture the flags. Do you guys go over like over the wire stuff?
No. Well, we talked about over the wire, yeah, but we didn't go over it.
So, if you guys aren't familiar with over the wire, it's a really good site, especially when you want to learn something or you're just getting started. It's basically a collection of different challenges, different capture flags or nodes. There's a specific set of challenges on there called Narnia. Narnia focuses around binary exploitation, and they're basically it's just a capture the flag challenge that gets increasingly harder. The whole thing is fairly introductory though, so there's no stack protection, there's no, well, we'll just see it. Okay, so while that is opening up, I'm going to get my cheat sheet here. All right, cool. So here's my, I'll let you guys kind of read through that while I talk about this. Okay, so when we're talking about basic exploits, we're probably, I'd say like 90% of the time, talking about basic overflows. So basically what this is if you picture a buffer, which again is really just a temporary space of storage, and let's say you allocate 16 bytes into this buffer, right? Okay, so you allocate 16 bytes and then you're telling the user to give you their name. You're assuming that the name is never going to be more than 16 bytes, which is just 16 characters. Well, what if the name is like 50 characters long and they have some super weird complex name? Well, what ends up happening there is that you fill up the 16 bytes that you originally allocated, and then it keeps going. Unless you have a check that says only take the first 16 bytes from their input and store it into this buffer, it's just going to keep allocating space. So what ends up happening is that you fill up that buffer and then you keep going into the stack and you start flowing into other things. So what you might end up flowing into is your registers. So you have your base pointer or your stack pointer, you might overflow that, or you give it like hundreds and hundreds and hundreds of bytes and you just keep overflowing into everything, and then you start overflowing other stack variables or other things. Basically anything that's accessible is fair game at this point. Well, one, if you're just a user that doesn't know what you're doing, you say, oh, I wonder if I can type this super long string into this 16-byte buffer. You're going to get a segmentation fault or a 6 error that you're typically going to get. What that means is that it tried addressing a space in memory that doesn't exist anymore, basically. And the reason it doesn't exist is because you overwrote the place it was calling to with like, I don't know, like deadbeat or something. Well, deadbeat is not typically a valid address in memory, so it says, okay, yeah, I'll point you there. Hey, that doesn't exist. I'm just going to stop you. That's essentially what happens. However, if you actually craft your overflow in kind of a clever way, you can actually overflow enough space in that 16-byte buffer, or past that 16-byte buffer, to where you fill a certain chunk of garbage, and then you can fill another chunk with like some shellcode that you wrote. And then after that, you're going to overflow the return pointer and point it to the beginning of your shellcode, and then it's going to start running down the stack. So you're actually going to start executing your shellcode. That's the basic gist of what a buffer overflow exploit is, right? So you have a buffer that you're going to overflow. You're going to fill that overflow space with some code, and then you're going to overwrite your pointers to point to the top of that code. And we'll get into this more when we start going over the NRT challenges. So that's basically that. Once you actually start overflowing into the stack, then you've successfully corrupted the stack and or the heap, and you're free to do whatever you want really within the bounds of other limitations that are set up by the binary or by the system or other things we won't really get. So I mentioned shellcode, and what this really is just that. The term stems from the fact that or the idea that when you're writing this code, the ultimate goal is to gain a shell from it, right? So if you can gain a shell, you can spawn a shell, you should have access to the computer as if you were actually sitting at that computer. So the code to spawn a shell is the shell code. Not very clever, but there you go. So I also mentioned that there are some limitations as to what you can actually do within the bounds of the binary system. So this is not a new thing. Obviously, these systems have been set up this way. C is like a super old language. So eventually people are going to say, hey, maybe the fact that you can just blindly copy data into a buffer is not a good thing. And even if someone doesn't catch that and they do, we should have another line of protection. Well, yes, this is where stack protection comes in. So three primary forms of stack protection that you'll see is ASLR, which is address stack layout randomization. And basically what this is you have your stack, you have your addresses in memory, and it literally just randomizes it. So every time you run, it's going to be a new address. So even if you manage to overflow your buffer and you know where your buffer starts, pointing to the top of that address won't mean anything when you rerun the program because it's a new address. It randomizes the stack on the new run. The other thing that you will often see is a stack canary. And really what this is just a value within the stack, and the preceding call will check whether or not that value is corrupted. If that value no longer exists, then it knows the stack was tampered with, and then it'll just throw an error input. The final thing that you'll probably see is dep/nx or dep/nx. What that stands for is data execution protection, and then no execution. So what that means is basically you just can't execute from the stack, right? So you can't put shellcode on the stack and then call to it because it won't execute. It turns that environment into not a read-only, but a read-write. It's not executable, right? So that's actually that's using ASLR and a non-executable stack. That combination is really actually pretty solid. As long as you build your program well and you kind of you know what you're doing, that's actually gonna mitigate a lot of different attacks. However, with everything, there are ways to get around that. So with ASLR, the one thing that you can do if you get lucky is actually just, instead of changing the value of a variable on the stack, just change the value or manipulate a variable or buffer that is on in global scope. So global variable, right? So why does that matter? Well, what's a global variable? It's accessible globally, right? Any function can call it. Okay, well, if we know that any function can call it, then that must mean it's static. Its address never changes. So even if you have ASLR, where the stack addresses are randomized on every run, that doesn't matter because every function needs to be able to access the address of its variable because that's what makes it global. So if this is always staying the same, you can put whatever you want in there and run all your stuff in other function calls, and then just always point to this one thing instead, right? So if your code is staying there, if your code lives there, then it'll be accessible throughout your program running. With a non-executable stack, that one's a little bit harder, but it's not impossible to get around. So we can't pull code off of the stack. We can't run code. So the key thing there is that we, as the attacker, we can't run code on the stack, but the stack can run code on itself. So I don't know if you guys are familiar with return to libc or ROP, return-oriented program. These are really the primary ways to get around this. So what return to libc is, you're going to overwrite the return address with the address of libc. And that's really like the primary library in C. Once you do that, you pretty much have free reign to call any function within libc. One of those functions is the syscall function. Well, cool, if I call syscall, then I can just push /bin/sh onto the stack. They can just push that, call it, cool, add a shell. That's it. And again, all of this is assuming that you are in a certain environment that your binary is set up a certain way, that the UID on the binary is a certain thing. There's a lot of variables that go into this that, again, I'm not going to get into because it's way, way out of the scope of this talk. But when you're just getting started, this stuff is really good to know. Especially when you're going over these challenges, you'll see a lot of that stuff, and you'll start thinking, okay, well, I have this roadblock, and this roadblock, and this roadblock. What tools do I have at my disposal? What do I know of that would allow me to effectively bypass one roadblock at a time to end up at my desired destination? Cool. Okay. So let's just talk about this quickly. Okay. So yeah. So as I mentioned, this is really, I mean, it's a game, is what it is, but it's super useful when you're getting started. You're going to see a lot of very common mistakes, I would say, that you're probably not going to see in the wild or really in real life, unless you're assessing an application that's just like complete garbage, and then at that point, like these people are just wasting money. So we can get in over here. So if you guys have done like Canvas or any of that stuff, that's all done through like the web UI. This is a little bit different. This you actually have to SSH in. And the password's just not answered. So there's a bunch of stuff in here that you can read, I guess, if you want to, but I'll just give you kind of the lowdown on this. So basically, you're dumped into an environment. You assume all of the binaries, the UID flag is signed from the next level. So Narnia 0's binary is signed by, has a UID of Narnia 1, Narnia 1 has the UID of Narnia 2, and so on. The reason that's important is because when you're actually running this, it's going to run as that user. So if your Narnia 0 binary has a UID of Narnia 0, well, that's great. You spawn the shell as your current user. That doesn't get you. So the rules of this are, you have a directory, so /temp, that you can write to basically as you wish. Then you have the /etc Narnia pass, which is going to have, so it's going to have Narnia 0 through 9, and this is what actually contains the flag. So the goal of all of these is to, so as Narnia 0, we want to get access to Narnia 1 flag, so on and so forth. And then you have the /Narnia directory, which is where all the binaries actually live. So the nice thing about this is that you get the binary and you get the code. So you don't have to like guess and check to see what's going on. You can actually just see. Okay. So first things first, let's just go ahead and run Narnia 0. Okay, cool. So correct value from 41441 to deadbeat. Alright, so let's just type in deadbeat. Okay, cool. And the value of val is still 41441, which is, I believe, capital A ASCII. Okay, cool. So let's take a look at the code. Okay. So, can you guys see that okay?
Yeah, there's no one to increase it.
Okay, so we have a long variable with the value of 4141. So that's what we want to override. And then we have a character buffer of 20 bytes, which is what we're going to be writing into. So then you have your printf function, which tells you what to do. Okay, then you have a scanf, which is 24s. That's 24 bytes in the form of a string, and then it's going to write that into buff. And then you're going to do other stuff. If the value is deadbeat, then it drops you into a shell. Otherwise, it prints right off. So, does anyone see what the problem in the code is?
carries 24 bytes into 20 byte buffer.
Exactly. Yeah. So that's basically it. So we're reading 20 bytes into, or sorry, 24 bytes into a 20 byte buffer. The other thing is, let's see. Yeah. So this is an X86 system running 32-bit little endian. Why that matters is, or sorry, the reason that matters is that, okay, so look at the order that these variables are declared. So you have your val first, and then you have your character array second. The reason that matters is because they're going to live on top of each other on the stack, but in the opposite way. So you would think, if you think of your memory segment, you would think, okay, you have 41441, and then you have your character buffer, so when it overflows, it's going to flow to this one. But it's little endian, so it's reverse. So actually you have your long, and then you have your character buffer, which is going to overflow to this one. And the other significant thing here is that it's exactly 4 bytes. Does anyone know how long the long is in the 32-bit architecture? It's 4 bytes. So that's kind of a deck giveaway. So you're gonna basically fill this buffer with 20 bytes of garbage, and then after that, you're gonna fill it with the value of ID. So let's do this. So Python dash C print, we'll say F times 20, and then we'll print okay. So what I'm doing here is this is going to print F, just the regular uppercase F 20 times, and then after that it's going to print MB, but it's going to print it as, it's going to print the hex value, not the literal strings. So when I run that, I should get that. So you can see at the end it's something weird because it's interpreting it as hex, not a regular ASCII value. So I believe if we pipe that into a 0. Okay, so it's still off. So why is it off? Yeah.
Because it's little endian and you entered that into Python as big endian.
Exactly. Yeah. So we need to reverse it. So again, it's little endian, and you can check how your CPU is set up just by that LSCP. So if we just reverse this, yeah.
You could also just use Python array slicing or whatever to reverse it. If you do
well, actually, I guess yeah, you can. That'd be an ugly slice. You can't. You would have to like split it at the \x and then reverse it. Because if you split the whole,
it treats the \x whatever as a single character.
Oh, really? Yeah.
Yeah, because that's just like a byte literal for
right,
a character literal.
Oh, that's cool. Okay.
Hey, I'm being helpful.
So anyway, yeah. So if we run this, then cool. Okay. It didn't do anything. So we check. Where am I? We're still non U0. So why are we still non U0? Does anyone know? Okay. Cool. Well, the reason we're still non U0 is because the program ran. It started up the shell, and actually I don't know. I don't know if you can see this. Okay, so that's the view message for everyone playing this now. So if you were running this on your system, which you can totally just pull these binaries or the code for these binaries and compile them as 32-bit and make sure you have the F no stack protection flag set. You can totally just do this locally, and then when you run vmessage, you'll actually see like the C7, which is the seg fault, the segmentation fault, saying that you overflowed the buffer, and then you'll actually see that the message was called. So that happened, and then it exited. Well, that doesn't really do us any good because we wanted to pause. So, what do we do? Well, the thing we can do is actually just interrupt it with another process. So, let's create a collection of commands. So, we're going to want to pipe this into Narnia 0. Then once that's done, let's call cat. Okay. So this is going to get piped over in that order. So when we run this, now we're Narnia 1. Cool. So now we can actually cat slash sweet. Okay, cool. So there we go. So we have the flag. So and then we can go ahead and log in as Narnia 1. Okay, cool. So I'm probably not going to go through all of these because
You're really hard.
I've been here for a while. But I will go through some of the more interesting ones. So let's see. Narnia 1 is actually probably Narnia 1 and Narnia 2, I would say, are the good ones. Okay, so let's just, I'll kind of explain as I go. So, okay, so give me something to execute in variable egg. Okay, so this is telling us that we have an environment variable named egg, and whatever value we pass into it is going to get executed. Cool, seems easy enough. So let's cat out 91.c. Cool. So okay, so we can see here we have our call to get in, and that's looking for egg, and then it's telling us to do that. So basically, if egg doesn't have a value, it's going to give us the message it gave us earlier, which makes sense because we don't have a value, and then it's going to exit. Otherwise, it's going to print that it's trying to execute whatever you have in end, and then it's going to get that value, store it in ret, and then call ret. So the thing here is, so you can see ret is a variable, but then we're calling it as a function here, right? So the reason it's doing that is because, and this is kind of a hint for the solution, we don't want to pass it just like bin.sh. That's going to do nothing. You know, bin.sh is not a function. 1. 2, it's a string literal, right? So it's literally going to try to run the function bin.sh, or really it's going to try to run the function allocated at the memory address for bin.sh, wherever that string goes on the stack. That's going to get you nowhere. What you actually want to pass it is a kind of a function pointer, if that makes sense. Cool. So if we want to get a shell, or at least want to get access to that password file, we're going to have to run some system command as Narnia 2, which we can do if we overflow this buffer because this is signed with the UID of Narnia 2. And we want to store that in it. So how do we do that? Well, we're actually going to have to write a bit of shell code. So we cd into temp, and then okay, so making new directory, and then just okay. So let's make a new file called shell. So, okay, this is probably going to get kind of confusing, and I'll try to cover everything to the best of my ability. So just try to follow this one. All right. So the first thing we want to do is actually set up this stack. And so okay, sorry, let me back up. So ASM is the extension for an assembly file, right? So what we're going to be doing here is essentially just running assembly. Once we have our payload, which is going to be the assembly instructions, we're going to build that, get the actual the bytes that make that up in hex. We're going to take that, and then we're just going to put that into the egg variable, and then when we run it, it should execute whatever we put in, right? So the first thing we want to do is clear out our accumulated register, which is EAX. An easy way to do that is just to XOR EAX with itself. Okay. And then we're going to want to actually push. We're going to want to push the location of where we want to, or what we want to access, the file we want to access. Okay, so let me push EAX, and then we're going to want to. Okay, so we're going to want to access slash, what is it? Let's see, slash RNA pass. So that's the location we want to access. So we're going to want that. Oops. We're going to want that in little endian as a hexadecimal character. So the way that we can do that is, so if we echo this out, if we echo this out to XXD, it should give us, so if I cut to XXD, it should give us, yeah, so that's what it is in, text. And that's great, and we just want that reversed. So the easiest way to do that would probably be to pass it to Python. And then print it out in reverse. Cool. So we have that. Oh, and actually, I'm going to take that and type it to sweet. Okay, so now we have this, and we can just we're going to have to chop this up into chunks. So just paste it out here, and then we copy and paste the whole thing. Oh, cool. So now we have this guy. Okay, so we have this. Okay, so we have our stack essentially set up. Now we're actually going to want to start pushing the location of where we want to go. And we want to put this in chunks. So we're going to push, and then we're going to do 8 of these at a time. So basically just chunk this entire thing up.
The second push command is spelled wrong.
Yeah. Okay, cool. That's done. So that was long. But basically what that is that's the path, as I mentioned, to our YouTube. And the reason we have it in this order is, again, it's a little lengthy, and so that's where we're gonna, so what we're gonna do is we're gonna open cat. We're gonna call, this is called a cat, and then it's gonna call here, this file, right? So it should cat that up the screen. The reason we put that in first is, again, it's a little lengthy, and so that needs to go before the actual call. And that's really just the argument as well. Okay, cool. So now we're gonna do some other stuff here. So we're gonna move ECX to ESP, and then I have to read my notes why this is the thing we have to do. Right. So this is actually something that tripped me up because I was not getting this word. So we're gonna want to call syscall, right? Syscall, when you actually see it in binary, is 80 in x80, x80. The calling convention for that uses a few different registers, ECX and ESP, and EAX, I believe, are some of those. So the data contained in each one of those registers actually maps directly to a different argument you pass the function. So the address for this file path is stored in ESP, right? And then the x86 syscall convention uses ECX as the second param, which the second param is going to be where we want the cat, right? Cool. So that's that. And then what we want to do is we're going to push EAX. And now we're actually going to push the binary we want to call. Okay. So we want to call /bin/cat, right? That's where the cat binary lives. So again, we do the same thing. On-dash-c /bin/cat. Little quotes. And then reverse it. Okay, and then pass that to x86. And here is the chunky one.
This is Python too.
Yeah.
You can do that encode task, I think, and that'll.
Yeah. Does it? Okay. So, well, no. Yeah. Anyway, so okay, so we have that, and again, we're just going to push all this onto the stack. So, and actually, I forgot we need 0x. Yeah. Okay, cool. And then again, we're gonna push. Thanks. Push this stuff. Cool. Okay. So we pushed the file we want to get out. We pushed the location to the cat binary. So now the only thing we need to do is actually execute syscall. Okay, so we have that, and then we're gonna move stuff into the proper registers so that syscall actually can access the arguments appropriately. So we're gonna put, not push. We're gonna move EDX or ESP into EDX, and then we're gonna push EDX, and then we're gonna move EDX, or sorry, ESP into EDX. Okay. So what I've done so far, actually, let me just finish this up and then I'll explain what I'm doing. Alright, so let me just make sure everything is right. Yeah, okay, cool. So, basically what ended up happening here is we're setting up the syscall so that it can access all the right stuff in the registers. And then we're also manipulating some of the registers, so we're either clearing them out or setting an appropriate value so that the syscall actually knows when it's doing and doesn't think we're passing any more arguments. This is essentially what is happening here. And then we're ending it with int 0x80, which is actually the call to syscall. So, all right, so we have this. There's a super real chance that this is not going to work.
That second to last line, you put a O instead of a 0 or a 0x.
Yeah, I think I could fix that.
The second to last line.
Oh,
For OXT, for the move AL OXT.
Yeah. Cool. Okay. So
Oh, probably work.
there's still a super real chance that this is not going to work, which is cool because this is totally probably.
which is the point of the game.
Yeah, pretty much. Cool. Okay, so now we want to build this, right? So, NASM or NASM, whatever you want to call it. We're going to call that, and then we're going to pass it out, and that's just the type of binary we're creating. So elf is executable in the file, I believe is what that's stands for. And then R. Cool. So now, actually, let's do this first. Okay, so now we have shell.o. So shell.o is actually a proper executable. So if we cat out shell.asm, we get what we just wrote, the assembly we just wrote. If we cat out shell.o, we get a bunch of garbage, which is expected. What we want to do is actually dump the binary. So we can just do dump dash s. Cool. So this gives us the stuff on the left is the address in memory, really just the offset from where the file starts to where it ends, and then all the stuff on the right is the actual text. So now we want to basically just copy and paste all of this, and then join it. So I think when I did this the first time, I wrote like a script that parsed all of this for me, but I don't have that on this computer, which sucks because that would save a lot of time. Okay, and then I'm just replacing the spaces with okay, cool. Step one. We have our shell code. Yeah. Okay. So what we want to do now is actually assign this to the environment variable heading. So, I believe we can just run export. I don't think I actually have that. It doesn't matter. So, I think we can just do export egg equals no, actually we can't. Okay. Yeah, so I forgot this one gets kind of weird. So the thing is, we need to pass this as actual hex, the hex interpretation of this string and not the string literal. So I think what we can do is this. Okay. So, the string, and then we can do
Should be able to do just ASM.decode X.
which on the. Oh, okay.
Yeah.
Well, that might be okay. Well,
Either, yeah, decode and then in parentheses, and then quote X. And then that.
yeah. So that is actually translating that. So what we want this is basically /x 31 /x C0, which is fine. So okay, so we can do this. Join, okay.
I don't think you need the second colon in the brackets. Like that? Yeah, you need those on.
No, okay, you know what, I'm just gonna do this manually. So, probably. Yeah, so anyways, I was saying, the reason we want this is because we actually wanted to interpret it as the actual, not the hex character, but the hex value. So that we want
encoding.
Yeah, exactly. You good? Yeah.
Pretty good.
Yeah, okay, cool. I was probably looking most All right. Good stuff. So, yeah, that's done. So now we want to assign that to X. So I believe we can just do export A equals, and we don't want to just pass this on because again, it's going to interpret the backslash X, whatever as the string literal. So we actually want to we want to give it the value as a binary, I guess. So a pretty easy way to do that is just to, so if you're not super familiar with the Linux environment, when you have $friends, basically what that means is that stuff is going to be interpreted and ran as like an actual command or a bash script, I guess, and then it's going to continue. So that means that the value of the bag is going to be equal to the output of this script. And then echo dash any, the n means a new line, so the null line, or sorry, not the null line, the new line at the end is not going to be added, which is what we want. And then e just means it's going to interpret the x/x, whatever, right? And then we get that. And hopefully, if we run Narnia 1, hey, there you go, so we have 1. Yeah, that's it. Because it's painful, and I probably should have prepared. Yeah. So that was a super, super long and probably super inefficient way to do all of that. But you get the point. So I'm not going to go through more of these because, yeah, we've been here for a while. So I guess wrapping things up. Yeah. So if you want to get into this, I would definitely recommend it. There's not enough people I think that do this well. So I was recently at kind of like an internal conference we do at my company, and I was talking to one of the guys at the in our exploit development team, and just talking to him and the stuff they do compared to like what we do is like we're not even on the same playing field. Like I'm sitting at work and like I pop web apps all day, and he's like, oh yeah, I write this terrible worm that I spread across a client somewhere because they wanted to do. So, you know, basically the same thing. But yeah, there's not enough people to do that, and it's super hard. And he kind of had this joke where he said that they should really put in the description that for that position that one of the requirements is self-harm, because you sit there for hours and hours and hours trying to get this one thing to work, and it's totally possible that it's just not, it's just not going to do anything. And then you're like, well, that was like 5 months of my life that I'll not get back. But that's a job. That's what it is. Yeah, there's a reason they pay pretty big bucks for this type of stuff. So yeah, that's pretty much it. Does anyone have any questions or anything?
Do you have the plug?
I don't actually.
Okay.
Yeah, I'm not really active on anything. That's something I should try to get on that something. It's not really. Honestly. Yeah, cool. I guess that's what it is.
Yeah, thanks. Do you have any other sites other than Over the Wire that you recommend?
I do.
Right.
I guess kind of shameless, somewhat self-promotion. So NCC Group, formerly Chicago office, has this website called Microcorruption. If you haven't checked it out, I 100% recommend it. So the idea is that you have some ARM device that's like a lock, and you're trying to break it, and they actually step you into this like little kernel thing, and you have some debugger that's all through the web interface. But it's like a real Texas Instrument like microcontroller with real assembly instructions. You can go to the website, look everything up, and you're essentially trying to do this stuff, but in a more real world application. So it's cool. I would definitely check that out. That's definitely worth a look. Yeah, if you guys have any questions, or you want to learn about this stuff, you can probably ping Mike and he'll get a hold of me, or come on and talk to me after this, and we'll figure something out.
You can, if you want to, you can write the site down on the board.
Yeah.
Write it down. Or we can even just pull it up on the.
Yeah, I can see that.
It's pretty fun.
So, microcorruption, exactly. Yeah. So you have to make an account and all that. But, yeah, there's a leaderboard. 1565, so if you need it, then congratulations, you might be behind.
Is it time off then at that point? Is it based off time?
No, I don't think it's that.
That teaches
You
from
saw
like
it
a
once,
beginner
then.
level.
Yeah, it's like super like what Narnia 0 was like, oh, overflow buffer to get this value. It's like even more simple than that. It's like run string to get this value.
Oh,
like,
Okay, so
right.
it shows
It
you
literally
how to get into it.
Oh, that's cool.
Understand what you're doing.
Yeah, it's like, yeah, it's really good. If you've never done any of this stuff before and you're interested, especially if your goal to learn all this stuff is to get into like embedded systems, this is like the place to go because this is literally putting you into an embedded system. So,
Yeah, it's pretty cool.